Have you ever wondered how someone predicts, say, the path of a hurricane? I mean, its intensity depends on wind speed, ocean temperature, and atmospheric pressure, all at once. They're not just looking at a single line of data. Nope, they're navigating a complex, multidimensional landscape. And today, we're going to build the tools to do just that.
This, right here, is the big question. It drives so much of modern science and business and, well, just about everything. Think about it. A company's profit doesn't just depend on its price, right? It's also marketing, costs, what competitors are doing. So how do you predict an outcome when dozens of things are all in flux? To figure that out, we actually need to start by looking back at a much simpler world.
So to build our new, fancy tools, we first have to remember our old ones. Let's take a quick trip back to the world of single-variable calculus. Remember when you had a function like y equals f of x? Life was pretty simple. You're basically on a straight path. For any one input x, you get exactly one output y. You can picture it as walking along a 2D line or maybe up a really simple straight hill. The only real question is, how steep is it right where you're standing?
And the tool for that, of course, is the derivative. It tells us the exact, instantaneous rate of change, the slope, at any single point on our little path. It's an incredibly powerful tool for sure, but it's built for a one-dimensional world.
Okay, so now it's time to leave that simple line behind and step into a much richer and, let's be honest, more realistic environment. You see, most real-world situations aren't simple paths. They're more like a landscape. Your altitude, let's call it z, it depends on both your east-west position, x, and your north-south position, y.
So here's the puzzle. If you're standing on the side of this mountain, what's the slope? I mean, if you face east, it might be super steep. But if you face north, it could be almost flat. Our old friend the derivative just can't give us a single answer anymore. We're going to need something new.
Our first step in figuring out this new landscape is to just map out the basic directions. And for that, we use a tool called partial derivatives.
The idea behind a partial derivative is actually pretty clever. We just pretend for a moment that only one thing is changing. We literally freeze all the other variables in place and find the slope in that one single direction.
Think of it like this. To find the partial derivative with respect to x, you take a giant slice out of the mountain running east to west, and then find the slope of that slice. To find the partial with respect to y, you do the same thing, but you slice north to south. We're just measuring the slopes in our main cardinal directions. But, and this is a big but, here's the catch. Knowing the slope to the east and the slope to the north is great, but it doesn't tell you the slope if you decide to walk, say, northeast. Partial derivatives, they only tell part of the story. To get the full picture, to understand change in any direction, we need to combine our partial derivatives. And that brings us to our next tool, the total differential.
This is exactly the question the total differential is built to answer. If I take a tiny step that moves me a little bit in the x direction and a little bit in the y direction, how much does my altitude actually change?
So the total differential gives us an approximation of this total change. The way it works is by assuming that for a really, really tiny step, the curved surface of our mountain is basically a flat, tilted plane. It just calculates the change based on that simple plane. And here's the best part. Look at how we build it. It's so intuitive. For step 1, you take the slope in the x direction and multiply it by how far you moved in x. Boom! That's the altitude change from the east-west part of your step. For step 2, you do the exact same thing for the y direction, and then for step 3, you just add them up. That's it. That's your total approximate change, dz. So far, we've only been talking about a single tiny step. But what if you're not just taking one step? What if you're hiking along a specific trail over time? For that, we need our final tool.
Right, so now imagine your x and y coordinates are changing continuously, maybe as a function of time. You're following a specific path on the map. We're not asking about the change from a single step anymore. We're asking about the rate of change of our altitude as we're hiking. This is the job of the total derivative. It uses the chain rule to cleverly combine the steepness of the terrain, our partial derivatives, with how fast our position is changing in each direction. What we get is a precise, instantaneous rate of change of our altitude along that specific path. Okay, let's put these two big ideas side by side, because it really helps. The total differential, dz, that's all about a single, static step. It gives you an approximation of the change. The total derivative, df over dt, That's about continuous motion along a path, and it gives you an exact rate of change. See the difference? One's a discrete step, the other's a continuous flow. So, we've journeyed from a simple line to a complex landscape. But why does any of this actually matter? Well, because the real world is all about these interconnected variables. And these tools are seriously everywhere. In science, if you have tiny errors in your measurements, the total differential helps you figure out the total error in your final result. In thermodynamics, it's the language of gas laws. In economics, it helps predict how demand changes when you mess with both price and ad spending. It is the core mathematics for any system with multiple moving parts.
So, there you have it. We've officially made the leap. We started with a simple derivative on a simple line, but by building up to partial derivatives and combining them into the total differential and total derivative, we've created this amazing toolkit to analyze and predict change in our complex, multi-dimensional world.
We've learned how to map the slopes and paths on pretty much any surface you can imagine, and it leaves us with this really fascinating question. Now that we have these powerful tools for understanding change, what complex system, what new intellectual landscape should we go explore next?